I know you all have been anxiously awaiting a new stats video, so I had to oblige, and I'm giving you a new stats video. Here we're talking about the binomial distribution, and you're going to notice some parts of this set of notes that are very familiar, and I'm going to show you a few calculator shortcuts, but we're going to make sure that you at least understand the mathematics behind what we have with the binomial distribution. So what we're interested in right here, we're going to talk about what are called Bernoulli trials. And a Bernoulli trial is a case where an experiment only has two possible outcomes, and we repeat that experiment over and over and over, flipping a coin, heads or tails. Those are the only two possible outcomes. You can see three more examples right here in these bullet points. We have testing the effectiveness of a drug. So it's either effective or it's not. Those are the two outcomes. Weekly sales for a car salesperson. They either sell the car or they don't sell the car. And then taste test for sodas. If you have two choices, they either prefer the first one or they prefer the second one. Those are examples where we're going to have binomial distributions. So the binomial distribution, the first thing about it, it's predicated on understanding of factorials. And I know we have seen factorials before. I know you guys have talked about factorials, hopefully in other classes besides this one. But we're going to do a couple of quick hand calculations for factorials. You can see the strict definition for a factorial is it's whatever that numerical value is times all the integers that precede it. Typically we ignore 1 because anything times 1 is going to be itself. So if we look at 3 factorial, that's just simply 3 times 2, which is 6. If we look at 4 factorial, that is 4 times 3 times 2, which is 24. And you might also want to note that 3 times 2 is 3 factorial. So we could express 4 factorial as 4 times 3 factorial, and we know 3 factorial to be 6. 4 times 6 is 24. And then our last one is 5 factorial. 5 times 4 times 3 times 2 is 120. Or we can express that as 5 times 4 factorial, and that's still 120 because it'd be 5 times 24. So there's your factorials. Now, binomial coefficients, this is something you've seen before without actually probably realizing we've discussed it. You have this notation, and it can be read as n choose x. Then there's your hint that you've probably seen this before. And it's expressed as n factorial over x factorial times n minus x quantity factorial. And on the calculator, that's the NCR, which we have done in the past. So NCR, and it would be n comma x. So we're going to do 2 by hand, and then we'll do the remaining 2 on the calculator. So the first one we have is 6 choose 1. So using the notation, 6 choose 1 is equal to 6 factorial over 1 factorial times 6 minus 1 quantity factorial. 1 factorial is just 1, so we're going to ignore that value. Then 6 minus 1 is 5. So this gives us 6 times 5 factorial. We'll simplify that numerator, or actually expand that numerator a little bit to give us something that we can cancel in the numerator and denominator. And we are left with 6. So if we look at part B, that's going to be equal to 5 factorial, 3 factorial times 5 minus 3. Okay, and here we can again expand the numerator till we get to a value that we can easily eliminate from the denominator. So the 3 factorials will cancel. And now we have 5 times 4 is 20 over 2 factorial, which is 2, and we get a value of 10. The remaining 2, like I said, we will do on the calculator. I just wanted to show you guys these because I will expect you to be able to do 1 or 2 maybe by hand. I understand the calculators do make this easy, but understand the mathematics is a lot more important than being able to just type it in on a calculator. So here on the calculator, we would just do NCR, and we're looking at, I have these written down, 7.3. So for part C, you would get 35. Then we would do NCR for part D, which is 4.4. And you should get 1. So there's those are your results for parts C and D, just using the calculator. And we will just go ahead and move on to what we mentioned earlier about the Bernoulli trials. So the Bernoulli trial, it's simply where you have repeated trials of an experiment, and it's called a Bernoulli trial if and only if the experiment has 2 possible outcomes. Typically we denote those as S for success and F for failure. The trials are independent, which means to say that the one trial does not determine the outcome of another trial. So you can think of flipping a coin. If I get a head on the first tail, or the first flip, then it doesn't affect the next coin toss. It doesn't change the value of the next coin toss. So we also have what's called the probability of success, or the success probability, and that is denoted with a lowercase p. And that success probability remains the same. It's consistent from trial to trial. So if we were considering flipping a coin, the probability of getting heads is 0.5. And that is consistent every single time we flip the coin. There is a 0.5 probability that we will get a head on any given coin toss. So with example 3, this is kind of a very long example, but it's a very detailed example that will expose you to what Bernoulli trials really are. So what we have is, according to tables provided by the National Center for Health Statistics in Vital Statistics of the United States, a person of age 20 years has an 80% chance of being alive at age 65 years. Suppose 3 people of age 20 years are selected at random. Part A, formulate the process of observing which people are alive at age 65 as a sequence of 3 Bernoulli trials. So each trial, I'm not going to write this out, so just listen on part A here. Each trial consists of observing someone who is currently alive at age 20, and then determining whether or not that person is alive at age 65. There are 2 possibilities. They are either alive or they are dead. So S is they are alive, F is that they are dead. And the probability for S is 0.8. So I will write that down. I'll write down a little bit of this here. So we have a success. Wow. There we go. Success is when the person is alive. And a failure is when that person is dead. And the probability of a success is 0.8. That was given in our information. But the process, though, I just wanted you to understand that how we established that. The next part, for part B, obtain the possible outcomes of the 3 Bernoulli trials. So we're looking at 3 individuals at a time. So the first thing that we have is that those 3 individuals are all 3 alive. Then we could have the instance where 2 of them are alive and 1 is dead. And we can repeat that for these 4 trials, or throughout these 4 trials right here. Then we also have the next condition where we have 3 failures. Then we may have 1 person alive. Okay, and there are the 8 possible outcomes. So we do have 8 possible outcomes. And we touched on this on Friday. We have 3 people, 2 possibilities of their condition, they are alive or dead. I wrote that down backwards. 2 possibilities of their condition, they're either alive or dead. 3 people, and we get 8. So that's one way you can quickly check whether or not you've come up with all the possible combinations. So then we want to determine the probability of each outcome in part B. So the first one is that the person, or all 3 people, are alive. And we can figure that out by the probability that the first person alive is 0.8, the probability that the second person alive is 0.8, and the probability that the third person alive is also 0.8. And I did not get my calculator out. So we would have that probability is 0.512 that all three people are alive at the age of 65. The next one that we have is a success, and then a failure. So that's 0.8, 0.8, and then the failure is 0.2. And that's going to be 0.128. And we can look at success, failure, success. Those values are the same as the previous one, just in a different arrangement. It'd be 0.8, 0.2, 0.8. So that is also going to be 0.128. And then our next one is a failure, a success, a success. So it's 0.2 times 0.8 times 0.8, 0.128. Then we have the probability that all three are failures. So that's 0.2, 0.2, 0.2. And we get 0.008. Then we move on to where we have two failures and a success. It's my dog making weird noises. Might have coronavirus. And we get 0.032. So then we would also look at failure, success, failure. Again, the values are the same as failure, failure, success, just a different order. So we get 0.032, and then we would have a success, a failure, and a failure. I'm just going to write it out. We don't need to. Again, still the same values, 0.032. For part D, find the probability that exactly 2 of the 3 people will be alive at age 65. So let's refer back to part C. Exactly 2 people being alive. That is success, success, failure, success, failure, success, failure, success, success. There are no other possibilities of exactly 2 people being alive at the age of 65. So we use the special addition rule that we have discussed previously. We would just add those probabilities together. Or since they are all 3 the same probabilities, we could just take the one probability and multiply it by 3. And we get 0.384. So there's a 38.4% chance that exactly 2 people will be alive at the age of 65 who are currently 20 years old. Attain the probability distribution of the number of people of the 3 who are alive at age 65. So this goes back to our discrete random variables that we've been talking about. So we have alive, we're going to call that little x, and then we're going to have the probability that x equals little x. So when we go look through here, there's 4 conditions. We have 0 people alive, 1 person alive, 2, 3, and that's it. So if we go back up to our table, the probability that nobody is alive is 3 failures. That's the only condition where we have that, so that's 0.008. The probability that 1 person is alive is, let's see, just 1 success, here, here, and here. We would add those 3 together, and it's 0.032 for all cases, so that would be 0.096. And then the probability that 2 people are alive, we just computed that in part D, so that's 0.0384. And then our last condition is that the probability that 3 people are alive, that is the single line at the top of our probability table where we have all 3 people being alive, and it's 0.512. The next thing that we want to talk about is the binomial probability formula. Now, had we known this formula prior to today, it would have made the Obama question on the test a much simpler thing to answer. So don't hate me. You still could have figured that one out without having this specific formula. And that's why I was really kind of relieved, I guess, that a lot of you did put a star on that problem. Several of you did trudge through it and give it a shot, and you got pretty close. But here is how you would have had to have come up with that. So when we have a Bernoulli trial and we're using the binomial distribution or the binomial coefficient, we're going to let n be the number of Bernoulli trials, and then s be the number of successes that we're looking for. So when we look at the table or the information that we had from the previous example, any particular outcome, we're looking at part 1 here, any particular outcome in which exactly 2 of the 3 people are alive at age 65 is going to be 0.8 to the second power times 0.2 to the first, which we end up with 0.128. If you look back up at our values that we computed, let's see, what I miss? Oh, sorry, that's just the probability, not exactly what I was trying to get at. The number of outcomes in which exactly 2 of the 3 people are alive, that's the one I was trying to get at. You have 3 outcomes, which we noticed earlier. So it's 3 times the probability that 2 people are alive. And when we take those, so here is the probability that 2 people are alive is 0.128. Notice we did have that 3 times. And in our probability table, we did 3 times 0.128, and we ended up with the 0.384. This formula, the probability formula, or binomial probability formula, will give us that answer directly without computing all of those values. It's 3 choose 2 times the probability of a success times the number raised to the power of the number of successes we're looking at, and then it's going to be the probability of failure raised to the remaining, which is the 3 minus 2, which would be 1. So we get 3 times 0.128 is equal to 0.384. This is the notation for that formula that I just mentioned, the binomial probability formula. And when we apply it, it's going to make a whole lot more sense. So we have the probability of our discrete random variable equaling some value x is equal to the number of trials in choose x. Then it's p to the x power. That's the probability of a success raised to the x power. And then it's 1 minus p, which is the probability. It ends up generating the probability of a failure to the n minus x power. And you can just type all that in, and you can generate the probabilities that you're looking for. So let's go to example 4 then, and that's where we apply this information. So we have the question is using the same data, and we're looking at the probability that exactly 2 people are alive, at most 1, at least 1, and then determine the probability distribution of the number of people alive at age 65. Sorry for the skip in the video, if there is one right here. I had to answer text messages from my child who is in the other room. So we're talking about using the formula, and for part A, excuse me, it's the probability that, my pen died, there we go. Probability that our discrete random variable is equal to exactly 2. So using the formula, we have 3 people to choose from. We are looking for 2 people being alive. And the probability of a success is 0.08. And we raise that to the second power because that's the number of people we're looking for. Then we have 1 minus 0.08. And this is going to be to the 3 minus 2 because that's our upper value on the binomial coefficient, and then the lower value on the binomial coefficient. And this is going to be equal to 3 choose 2 is, the dogs are going crazy, should be 3. I'm just going to double check, make sure I'm not losing my mind. So that is 3. Then 0.8 to the second power. I'm doing this step by step. You guys can just type this all in one string on your calculator and come up with the value. And then 1 minus 0.8 is 0.2. 0.2 to the first power, I don't know why I even bothered to try to type that, is 0.2. So when we multiply these together, we get 3 times 0.64 times 0.2, and we get 0.384, which is exactly what we computed earlier by using the addition formula. Here is just one straight formula that will allow us to calculate this sometimes more quickly than using the addition formula. Part B is the probability that our discrete random variable is less than or equal to 1. So that's the same as the probability that x equals 0 plus the probability that x equals 1. And when we compute those values, probability that x is 0 is going to be 3, choose 0, 0.8 to the 0 power, times 0.2 to the third, 3 minus 0 is 3, plus 3, choose 1, 0.8 to the first power, 0.2, 3 minus 1 is 2, and we will type this in and simplify it. Let's see. We get 1, 1, 0.2 to the third is 0.008 plus 3, 0.8 and 0.04. Multiply these together, we get 0.008 is the probability that x is 0, and then the probability that x is 1 0.096. Add those together, 0.104. So that is the probability that x is less than or equal to 1. So you could have 0 people or 1 person alive. There is a 10.4% chance of that occurring. Part C, we will give Jamie credit for recognizing this so astutely the other day in class. It's the probability that x is greater than or equal to 1, which means we have the probability that x is equal to 1 plus the probability that x is equal to 2 plus the probability that x is equal to 3. Well, if you notice, the only value we didn't include is the probability that x is equal to 0. So we know that the sum of all probabilities is supposed to be 1. There's only 4 options for our probabilities in this particular problem, 0, 1, 2, and 3. So we can simply just say this is also 1 minus the probability that x equals 0. We know that probability from our previous example. It's 0.00, or previous part of this example. It's 0.008. So we can just write this as 1 minus 0.008, and we get 0.992 as our probability that at least one person is alive at the end of or when they're turned 65. So at least one person out of our 3 people will be alive is 0.992. Part D, determine the probability distribution of the number of people alive at age 65. We have the probability for 1 being 0.99 or 0.096, probability of none, the probability of 2. The only thing we need to do is compute the probability of 3, and then we can complete our table. So I'm going to do part D right over here off to the side. So we're looking at the probability that x equals 3. I'm going to do 3, choose 3. Success probability is 0.8 to the third power. Our failure probability is 0.2. 3 minus 3 is 0. So 3, choose 3 is 1. 0.8 to the third is 0.512. 0.02 or 0.2 to the 0 power is 1. So we have a probability of 0.512 that the 3 people are alive. And now we can write out our table. We have X, and this should line up with the table that we generated earlier. If it doesn't, then I've made a terrible mistake somewhere. Probability of 0 was 0.008. We found that right here. The probability of 1 is 0.096. The probability of 2 is what we calculated in part A. And the probability of 3 is 0.512. So we used the binomial distribution formula, and we came up with this probability table. If you look up at the probability table we generated earlier using the addition formulas, we have the exact same values. The next thing that we want to look, well, here's probability tables. You can read through this. Probability table kind of shows you your n and x values. It gives you the probabilities up 1, 0.1, 0.2, 0.25, and so on. It kind of is a handy tool to have sometimes when the probabilities are relatively small or your sizes of your population are relatively small. The shape of binomial distribution, generally it's right skewed when p is less than 0.5. It's symmetric if p is exactly 0.5, and it's left skewed if p is greater than 0.5. So our problem when we looked at the mortality rates, the person being alive at 20 and then also being alive at 65, the probability there was 0.8. So 0.8 is certainly greater than 0.5, so that means that our data that we were just looking at for the person being alive at 65 is going to be left skewed because its probability is greater than 0.5. Mean and standard deviation of binomial random variable. There's 2 formulas here. Mu is the number of trials times the probability, and sigma is the square root of the number of trials times the probability of a failure. So we're going to see that in example 5, and this will be the end of this set of notes. Find the formula again here, so I don't have to scroll back and forth. Okay. So to find the mean, so mu is equal to n times p, and in the case of this problem, the number of people that we have are 3, and the probability of success is 0.8, so we multiply that together, we get 0.24, or sorry, 2.4. So there's our mu, or our mean, and then our standard deviation is the square root of np times 1 minus p. I don't know why I made that so long. np we calculated for our mean, so we could also say that this is equivalent to mu, so it's going to be the square root of 2.4, and then 1 minus 0.8, which indicates our failure probability here, is 0.2. So we get 2.4 times 0.2 is going to be 0.48, and then when we take the square root of that, it is 0.693. So there's our standard deviation. The hypergeometric distribution, we're not going to talk about the hypergeometric distribution, but what we want to know for the purposes of this class is that the binomial approximation is fairly close to the hypergeometric distribution. Hypergeometric distribution is well beyond the scope of this class, so it's not anything we're going to have to really worry about. This is, yeah, that's it. So we've covered all the examples in the notes. I'll answer any questions you guys may have in class. I realize there's a high probability with it being 9:40 that nobody's going to watch this video tonight. So we may be discussing it in class anyway tomorrow. What I probably would like to do though is go over homework questions from 2.1 and 2.2. and then we'll look at this. But this is your video. Hope you guys are having a great weekend, and I will see you in the morning.